Welcome back. In the last chapter, we explored what black holes are. We learned that a black hole is not a hole in space but an incredibly dense object whose gravity is so powerful that nothing, not even light, can escape once it crosses the event horizon. We also discussed why black holes are invisible, how scientists detect them, and why they are among the most mysterious objects in the universe. But this raises an important question. Where do black holes come from? They don't simply appear out of nowhere. Every black hole has a beginning, and its story starts with one of the most beautiful objects in the universe, a star. Every star you see in the night sky is essentially a gigantic ball of hot gas, mostly hydrogen and helium. Our own sun is a typical star, about 4.6 billion years old, and it shines because of a process called nuclear fusion. Deep inside the sun's core, temperatures reach around 15 million degrees Celsius. Under these extreme conditions, hydrogen atoms collide and fuse together to form helium. This fusion releases enormous amounts of energy in the form of heat and light. This energy is incredibly important because it creates an outward pressure that balances the inward pull of gravity. Think of a star as being in a constant tug of war. Gravity is trying to squeeze the star inward, while the energy produced by nuclear fusion is pushing outward. As long as these two forces remain balanced, the star remains stable and continues shining for millions or even billions of years. However, stars do not have an unlimited supply of fuel. Eventually, they begin to run out of hydrogen in their cores. What happens next depends almost entirely on one factor: the star's mass. Small stars, including those somewhat smaller than our sun, live for incredibly long periods because they burn their fuel slowly. When they finally exhaust their hydrogen, they expand into red giants before gently shedding their outer layers into space. The remaining core becomes a dense object known as a white dwarf. These stars never become black holes because they simply don't have enough mass. Stars similar to our sun follow a similar path. In about 5 billion years, our sun will expand into a red giant large enough to engulf Mercury and Venus, and possibly Earth. Eventually, it too will leave behind a white dwarf. Although this sounds dramatic, the sun will never become a black hole. The story becomes much more exciting when we look at massive stars. Stars that are at least 8 times more massive than the sun live much shorter lives. Because they contain more mass, gravity compresses their cores more strongly, causing nuclear fusion to occur much faster. As a result, these giant stars burn through their fuel in only a few million years instead of billions. As fusion continues, these massive stars create heavier and heavier elements. Hydrogen becomes helium, helium becomes carbon, carbon becomes oxygen, and the process continues until the core is filled with iron. Iron presents a major problem. Unlike lighter elements, fusing iron does not produce energy. Instead, it consumes energy. Once a massive star develops an iron core, nuclear fusion can no longer support the star against gravity. At this point, gravity finally wins. In just a fraction of a second, the core begins collapsing inward at astonishing speed. The collapse is so violent that the outer layers of the star crash into the collapsing core and rebound outward in one of the most energetic explosions in the universe, a supernova. A single supernova can briefly outshine an entire galaxy containing hundreds of billions of stars. During this explosion, many of the heavy elements found throughout the universe, including gold, silver, uranium, and many of the atoms in our own bodies, are scattered into space. In a very real sense, the calcium in your bones and the iron in your blood were forged inside ancient stars that exploded billions of years ago. As the astronomer Carl Sagan famously said, "We are made of star stuff." After the supernova, the fate of the remaining core depends once again on its mass. If the leftover core contains roughly between 1.4 and about 3 times the mass of the Sun, it becomes a neutron star, an incredibly dense object where a teaspoon of material would weigh billions of tons on Earth. But if the remaining core is even more massive, not even the pressure between neutrons can resist gravity. The collapse continues without stopping. The core shrinks smaller and smaller until it forms a black hole. The event horizon appears, permanently trapping everything within it. From that moment on, the newborn black hole begins interacting with the surrounding universe. It may slowly consume nearby gas, orbit another star, merge with another black hole, or remain relatively quiet for millions of years. This remarkable journey, from a cloud of gas to a brilliant star, then to a spectacular supernova, and finally to a black hole, can take millions of years, yet the final collapse itself happens in only seconds. It is one of nature's most dramatic transformations and reminds us that even the mightiest stars are not eternal. In the next chapter, we'll explore the different types of black holes, from stellar mass black holes only a few times heavier than our Sun to supermassive giants containing billions of solar masses that lie at the centers of galaxies, including the one hidden at the heart of our own Milky Way.